Okay, let us move on. So this is lecture 1.2, the continuation of lecture 1. And without understanding how the magic happens, let us look at a circuit with AC sources or one AC source. So suppose we have a resistor, and an inductor and a capacitor as we drew in lecture 1.1, and then we have a voltage source which is sinusoidal, and say the source is cos t. So what is here? So when we only write cos t, what is the coefficient with t here? It is 1. So although we have not written it, but everybody understands this is a 1 here, and though we have not written here, it is a 1 here as well. So if we again plot it, plotting is a very important tool and skill for an engineer. So you should understand how we plot cos t. So cos starts this way, goes down, comes up, and then repeats itself. So what is this value of time after which it repeats itself? And you should know it is 2 pi, and this is the half of it is pi, and at pi it is minus 1, uh, minus 1, and at 0 cos 0 is 1. So it is basically a signal or a source that oscillates between 1 and minus 1. And this time, the total time it takes for one cycle to complete is the time period, and the reciprocal of this is basically the frequency. So the frequency of this signal is 1 over 2 pi cycles per second or hertz. And the time period is in units of time, which in this case is 2 pi seconds. So when we have 1 here, the signal oscillates between 1 and minus 1. When we have a 1 here, its time period is 2 pi. So let us stick with that and move on. So suppose this is a voltage source. So we are told that this is a source voltage small Vst is the function f of t that we are dealing with. Vst here and t is here. Remember, we don't have when we don't have anything else except cos t written, then it is an eternal signal and it continues from minus infinity and up till plus infinity. It is an eternal signal. Eternal functions are those that starts from minus infinity and goes all the way up to plus infinity. However, in circuit analysis, we usually are not concerned with the past. Usually, all we want to know is the state of the circuit at that time we get interested in a circuit, and what is going to happen later on. So that is why we put a ut here. So when you see a ut, it means that this thing starts at t is equal to 0, and it is 0 before that. So it is not an eternal signal now. So in all the circuits usually we deal with have this ut explicitly specified or implicit. Suppose this is a value of 1 ohm, or let us for generality take it a resistor of 4 ohm resistance, and let us say this is a 2 Henry inductance or inductor, and this is a say 0.25 0.2 farad capacitor. If I tell you to find this I, okay, let us add something here as well, so that it turns into a circuit that we cannot solve with our current knowledge. That's the objective right now. So suppose this is a capacitor of say 1 farad capacitance. Now we understand that this is not a series RLC circuit. It is not a parallel RLC circuit. This is not in parallel with this one or this one. And this is not in series with this one either. So it is a circuit we are not familiar with. And if I tell you that in the AC analysis of circuits that we are going to study, there is a magic, there is a magic that happens somewhere here. There is a band of magic. So this everything related to this circuit with a t in it, with a time in time, or this circuit is in time. So this voltage source is a function of time, and this current that we are going to find is also a function of time. So whatever is happening here and is told to us in the time domain, due to some magic, get transformed to something like this. The circuit layout remains the same. Sorry, we have a capacitance here, a capacitor here, and a capacitor here. Now, because of this magic that we are not familiar with right now, and obviously we are going to study that in detail, but if I tell you that somehow this cos of t transforms to, and this VST transforms to a capital VS, and this cos of t transforms to 1, that's it, only 1. And so it is not a sinusoidal voltage source anymore. And this 4 remains 4 ohms. This 2 Henry transforms to 2 iota ohm. It's not in Henry any longer. And what is iota? I hope you remember from your maths knowledge. Iota is the square root of -1. It is an imaginary number, does not exist in real life actually, although it has several meaning and interpretation. But right now, this is all we want to know. Square root of -1 can't be computed, and it is denoted by iota. So this 2 transformed through this magic to 2 iota, and this Henry transformed to ohm, and this 0.2 farad transformed to 1 over 0.2 iota ohm. So now this is something in ohm. This is something in ohm. This is something in ohm. And similarly, 1 over, this was 0.2 transformed to 1 over 0.2. So this is 1, this is transformed to 1 over 1, which is 1. And with an iota here as well, and ohm. Now, can you tell me that when this whole circuit was given to us in the time domain, would any one of you uh, take a parallel equivalent of these two by, say, multiplying these two and adding these two in the denominator? So 2 multiplied by 1 divided by 2 plus 1, like we take the parallel equivalent of two resistors, say a 2 ohm resistor and a 1 ohm resistor. So we have a product over sum formula which says 2 multiplied by 1 over 2 plus 1 is the equivalent resistance of this parallel combination, which in this case is 2 by 3. So the equivalent resistance must be smaller than the smallest. So 2 and 1 is smaller. The equivalent is this smaller than the smallest value. So can someone come up and say, okay, these two are in parallel, so we are going to get 2 into 1 over 2 plus 1 is equal to 2 by 3 watt. What here? This is in Henry, this is in farad, so we cannot do this. We cannot do this. Remember, when two things are of same unit is when we can operate on them in the same way. So now look at what this magic has done to this circuit. This was in ohm already, it remained in ohms. This was in farad, turned into this quantity is in ohms. This quantity 2, which was in Henry, now transformed to 2 iota and in ohms, and this in ohms too. All these are in the same unit, same type of quantity, except that this is a real quantity, this is an imaginary quantity. These are imaginary quantities, and this is a real number as well. So we had a volt here, everything written, and a volt at the end. That volt remain the same. So now this is a DC source, let us call it this way, of 1 volt, and all these ohms. So what do we get? Consider this circuit as a resistor, a resistor, a resistor, and a resistor with a DC source of 1 volt. So this is 4 ohms. This is 1 over 0.2, which is 5. And 1 over, remember this 1 over iota is minus iota. I think it's very simple. You can solve it yourself and see. So this is minus 5 iota ohm. This is 2 iota ohm. And this is minus iota ohm. So all these are resistances now in ohm. This is real, these are imaginary. And see, the capacitors converted to negative values, and the inductor converted to a positive imaginary value. So how many of you, ignore these imaginary terms for a moment, how many of you cannot solve this circuit and to find, say, this current? So let us mark this current clearly as this current, or the current flowing in the source. This is IT, not this one. This looks like a mesh current flowing into this as well, but no, this is this current, and we have to find this one. How many of you, this IT is this, remember this small vs converted to capital Vs, this small I will convert through that magic to capital IS now. So how many of you cannot solve this circuit where all these are resistances, and for a moment assume all these are real values? How many of you cannot solve this? If there is someone who cannot solve this circuit to find this IS, should not be in ENA. He or she should go and repeat that LCA, because this is what we have been studying in LCA, and we started LCA with this. It's a simple circuit. So for example, if I have to solve now, I can do this. Had these been two real values, I would take the equivalent, parallel equivalent, then all these will be in series, and we can sum that up, and then this IS would be equal to, so IS would be, look at this, IS would be equal to this voltage 1 divided by the equivalent resistance of this network, where these are in parallel. So 2 iota in parallel with minus iota. So this thing has to be resolved. Then we are going to get the equivalent of these two. So one resistance here, that equivalent one, and all these in series. So plus 4 plus minus 5 iota is the total equivalent resistance in ohms. So 1 volt over this ohm is the current in amperes. Is this something difficult? So we can do this. And by the way, you should be able to do this, because based on your study and knowledge you have acquired in FSC or A levels, what are these things going to become? Complex numbers. And you should revise everything about complex numbers. The book that we have been following in LCA is the course book for ENA as well. And in the book, I think there is an appendix that discusses complex numbers, so you can revise using that, or you can revise using your own FSC or A level books. But we need a very few things to understand how to handle the complex numbers. So someone who is familiar with complex numbers and can use the calculator adequately for complex numbers can very easily solve this denominator term, and a resultant complex number will come here. So 1 divided by a complex number, if I can handle that, IS is going to be a complex number, and we are going to get that. So while this sinusoid resulted in a real number, the current is not a sinusoid like this. It is a bit different. How much different is that? Let us revise these complex numbers a little, and then you can see what IS would be. But remember, we are in the magic land. We are doing this in the transformed world. Transformed domain. This is time domain, this is transformed domain. And the transformation occurs through this magic band. So this transformation is yet to be understood. But something that we don't know right now, I know of that, and you are just made to believe, imagine there is something that does something, is it, there is a law, there is a rule according to which I wrote this as this as this as this, and you are going to learn that very easily soon, inshallah. But after this transformation, we have to solve this circuit, which is a very familiar circuit based on our LCA knowledge. The new thing that came up is how to handle complex numbers. Once we know that, we are going to very easily solve this. And what we need to know of complex numbers is a few simple things. So suppose we have a complex number. Let me revise it here. Then we will solve this. So let us mark it out. And then after revising the complex numbers here in this small space, we are going to again solve this. So what do we get? So in complex numbers, so suppose Z1 is a complex number. You know, a complex number has a real part and an imaginary part. This way of writing a complex number is called the rectangular way of writing the complex number. There is another way of writing a complex number. So we can write this same complex number as a value R with an e raised to the power iota theta 1. This is the polar form. This is the rectangular form. This is the polar form of a complex number. Remember, I hope you still remember this complex plane. The complex plane. This is the real axis and this is the imaginary axis. The iota values come here on the y-axis and the x-axis is used for real values. So this is a real value x1. So if x1 is positive and this is x1, and if y1 is positive, say this is y1, then this point in the complex plane is this z1. And so basically x and y are the x and y components of this z1. And this distance from the origin to z1 is r1, and this angle is theta 1. So you see, in the polar coordinates, we need this direct displacement r1 and this angle from the positive x-axis. These are the two forms in which we represent and show the complex numbers. So this is how a complex number is. So the other thing we want to know is, suppose we have another complex number x2 plus iota y2, can also be written as some r2 e raised power iota theta 2. There is another way of writing this polar form. Instead of writing e raised power iota in all complex numbers, we replace them with the sign of an angle. So angle theta 1. It is still the same as this one, but it's easier to write. So R2 angle theta 2. So now we have a complex number Z1 and a complex number Z2. What we want to revise, what we should be revising are how these two complex number add together, subtract together to get the new thing. So the real parts add together or subtract in the same order to get the real part of the resultant, plus the imaginary parts are added or subtracted as required in the same order with an iota here. So this is the imaginary part, this is the real part. These are how complex numbers are added or subtracted together. And we should also like to revise how are complex numbers multiplied together, multiplied or divided. So Z1 multiplied with Z2 or Z1 divided by Z2 is something that is easier done in the polar form than in the rectangular form. Addition and subtraction is easily done in the rectangular form, and multiplication and division is more easily done in the polar form. So Z1 multiplied by Z2 is R1 multiplied by R2. And if Z1 divided by Z2 is done, then R1 divided by R2 is being done. And the angle, if multiplication is done, the angles are added. And if division is done, the angles are subtracted. So this much knowledge is critical for everyone to know about complex numbers, how they are added together. Why? Because what we are going to do here, we are going to add and subtract them, multiply and divide them. So this knowledge is critical for you to be revised. And once you do this, you can very easily solve this. So there is okay. Um, I think you can do this for your with your own understanding and with your own on your own. But let me just assume that you have revised complex numbers and understand what I am going to do further, and you should be able to comprehend that. So I am completing this clip here.